Hi everyone, in this video we're going through integration by recognition. In your textbook it is in 11H, although it's not specifically called integration by recognition, it's just called miscellaneous exercises. So we're going to do two examples today, two from the textbook, and then we're going to have a look at a past VCAR question. You'll see them, these types of questions on past VCAR papers. Exam 1, because it's, exam 1 focuses on skills, and if you could do this on your calculator, there wouldn't be any point on doing integration by recognition. But they don't explicitly say integration by recognition, so you can often tell that you're using this process because of the way the questions are structured. So we'll do that question from, I think it's the 2017 VCAR paper, and then we'll do the question that was also on your trial exam. All right, I might actually save because this computer has been very glitchy. All right, so everything's saved and ready to go because I hate it when it dies on me, and if I haven't saved it, that's always problematic. Okay, so look at how this question is structured. So we've got f of x equals log base e of x squared plus 1, and it says show that. So you need to be familiar with show that question, so it's good that we're doing one today. So we're given the answer for the derivative. So all we have to do is get the derivative, all right? Just treat it as you would, as if it said find the derivative of f of x. The reason why we've been given that derivative is to go on to do B, which is find that definite integral. And what we do to find that definite integral is we use that derivative or our answer from part A. Okay, so let's do part A first. Let me just get my pen ready. Okay, so our function f of x is equal to log base e x squared plus 1. Actually, this was a question on your trial exam, I think the very first one, which is interesting. So it's probably good that we're doing it here as well. Okay, so I'm just going to use the chain rule. So let u equal x squared plus 1. So that means y is equal to log base e of u. So du dx equals 2x and dy dx equals 1 on u. And when I substitute u back in, I get 1 on x squared plus 1. So your derivative, f dash x, is 2x over x squared plus 1. Now for question B, and most of you did that quite well on your trial exam, but you can have a look at your trial exam. Question 1 was exactly the same question. All right, hence evaluate this definite integral. So you can see what we have to solve for. Actually, I might do this in no, I'll do it in blue. Our terminals are from 0 to 2, and we've got x over x squared plus 1. Now, when you write a definite integral, or an integral, doesn't have to be a definite integral, make sure you put dx on the end, all right, because you'll get it wrong. All right, so don't forget the dx. I saw that on a few trial exams. Okay, so we've got to compare this answer, all right, to this. All right, so how do they differ? So basically, we've got 2 is multiplying this x. So I'm going to put the 2 there. But just to counteract that, I multiply it by a half. So I'm going to put the half out here. So when I multiply that half by 2, I'm not really changing that definite integral. Okay, I've just now got it in a way that looks the same as our derivative that we had in part A. So if I rewrite that, I'm going to have the half out the front. 0 to 2 on 2x x squared, plus 1 dx. Now, I know from part A that my derivative is 2x over x squared plus 1. So my antiderivative of that is my original function, which is log base e x squared plus 1. All right, so we're finding the antiderivative of 2x over x squared plus 1. So we found the derivative in part A, so the antiderivative is the original function, f of x. Don't forget that half out the front, and then our terminals 2 and 0. So let's go and do that. I'll see if I can fit it all on one page. Go up here. Half log. Oh no, I'm not going to have enough room. Start again. And do it down here. Half log base e, substitute in the 2, and then minus log base e, 0 squared plus 1. Scroll down a bit, just make sure I've substituted that incorrectly because I felt like that was very quick. Alright, so we've got half log base e 5 minus log base e of 1. Alright. Now, when your argument is 1, that's going to be 0, so we're just left with half log base e of 5. Because this, when you have your argument is 1, so the 1 in the brackets, that's equal to 0. So your answer is a half log base e of 5. All right, with the next example, before we move on to a VCAR question, I am going to play you this example from the textbook. Okay, so it doesn't go for too long. It does refer to trig identity, so I might explain this trig identity to you after the video. So I'll press play.
What we ultimately want to be able to do here is integrate this function here. The problem is, though, we don't have an ability to integrate a function that looks like this. So what the question has asked us to do is first derive this function and then use our answer from here to help us to integrate this function over here that we otherwise wouldn't be able to do. So to start off by showing that the derivative of this equals -1 on sine squared x, we're going to start with f of x, and then using quotient rule, we're going to derive it. So the derivative of u, the numerator here, is negative sine x, multiplied by v is just sine x. Subtract the derivative of v, so the derivative of sine x is cos x, multiplied by u, the numerator, is cos x, all over v squared is sine x all squared. When I tidy this up, I end up with negative sine squared x minus cos squared x, all divided by sine squared x. Now the question gives you a bit of a clue as to where we're heading with this numerator here. If I pull out -1 as a common factor here, you can see I create sine squared x plus cos squared x, and now I can replace that expression there with 1. And thus I now have what the question has asked of me, which is the derivative of cos x over sine x. Now it says hence evaluate, so we're going to use this information here to help us evaluate this integral here. Now it's asked us to integrate 1 over sine squared x. I don't have 1 over sine squared x, I have -1 over sine squared x. So I need to manipulate this so it looks like that. So if I multiply this expression here by -1, that will give me what I want. But I also have to multiply it by -1 again so that I'm not changing the value of what it is I'm trying to integrate. So these two parts multiplied together gives me this here, and I'm left with that -1 out the front. So if I pull it outside of the integral, I end up with this expression here. Now this is something that I can integrate because I know that the integral of this expression here will give me my original function plus c. But given that we're integrating this between two terminals, I don't need to worry about the plus c. So the integral of -1 over sine squared x between the terminals of pi on 4 and pi on 2 is cos x divided by sine x with those terminals sitting on the end there. Now to evaluate this, I need to substitute pi on 2 into this expression and then substitute pi on 4 into this expression. Cos of pi on 2 is 0 and sine of pi on 2 is 1. Cos of pi on 4 is root 2 on 2 divided by sine of pi on 4 is also root 2 on 2. So I end up here with 0, subtract 1. Remember, we've also got that negative out the front there. So this entire integral is equal to the value of 1.
All right, so you're probably wondering the sine squared x plus cos squared x. So we do have trig identities, which we don't really cover in methods, but this is probably the most common one. So I might just quickly get a new page up just to explain how this one works. So the main trig identity that you should know is tan theta equals sine theta over cos theta. Now, you should also know that, according to SOHCAHTOA, so remember SOHCAHTOA that you learned when you did trig back in year 9, we have opposite over adjacent. So if you think of your triangle, your right angle triangle, and we'll put theta here, and let's just say it's on the unit circle, so it's got a radius of 1, and sine is your opposite side, so sine theta, and cos is your, what do we call it, adjacent side. Okay, so if we use Pythagoras' theorem, so you know a squared plus b squared equals c squared, so we can label it, and it doesn't matter what we label a or b, but let's just stay consistent with the way it's written. So a squared is sine, so a is sine theta. Now when we squared sine, we always put the square in there. So remember that sine squared theta is equal to sine theta times sine theta. Okay, so we're squaring sine theta basically. Plus b squared, so cos squared theta, and then 1 squared, which is just 1. So that's where that trig identity comes from. So if you do need it, sine squared theta plus cos squared theta equals 1. Now there are other trig identities. If you're interested, you can do a quick Google search, but I don't think they're not on the course and you don't need to know them. All right, let's get back to our questions. Not that one. Where are we? This one. Okay, so on a past exam paper, this was from 2017, so we've got y equals x times log base e of 3x. So we've got to find dy dx. And then we're going to use that answer, and it hasn't said, it's not a show that question, which is a bit annoying. But if it is if it isn't a show that question, you just keep working even if you got it wrong, because you can get consequential marks. So in part B, see how it says hence calculate. Usually if you see the hence calculate part, so the word hence, meaning therefore, means you have to use the previous answer. So hence calculate this. Express your answer in the form log base e of a, where a is a positive integer. Now I think that might be it for that question. So maybe have a go at doing it on your own. And then when you're ready, you can press play. All right, with this derivative, we're going to use the product rule. Okay, so we're going to let u equal x and v equal log base e of 3x. So dv dx is equal to 1 on x. Make sure you know the rules for derivatives. Actually, I think some are on your formula sheet. I don't have a formula sheet nearby to check. And then du dx is equal to 1. So with your product rule, it is on your, what do you call it? Formula sheet. Okay, so it's x times 1 on x, which is x on x, plus 1 times log base e of 3x. So we've got 1 plus log base e of 3x. And we're finding the derivative. Yep, so that's all good. Can't simplify it any further. All right, so for question B, it says hence calculate this definite integral. So you can see what we have here, log e of 3x plus 1, is what we found in the previous question. So I just had it the 1 on the other side. We have to express our answer in the form log base e of a, where a is a positive integer. So just remember that's helpful. Maybe helpful, maybe not helpful, don't know until we do the question. Okay, so we're going to find the definite integral from 1 to 2 of log base e 3x plus 1. Make sure you put the dx on the end. So we know that the derivative is 1 plus log e 3x. So the antiderivative of that is our original function, which is x log e 3x. Log base e 3x. And we're going from 1 to 2. All right, so we're going to substitute those terminals in. So 2 log e, 3 times 2 is 6. And then we've got minus 1 times log base e, 3 times 1, which is just 3. I'm going to get rid of that 1 out the front because it just looks a bit weird. All right, and it looks like my L's are my 1s. Okay, so with this one here, remember when you've got the same base and you're subtracting, you can you divide, so using your log laws, but that 2, first of all, I need to just bring that out, the power of 6. So this 2 here becomes squared there. So we're going to have 36. My dog just sighed. I'm boring her with a bit of integration by recognition. All right, so because we've got the same base, we can actually divide our arguments. So 36 on 3. So that's log, and 36 divided by 3 is 12. All right, so there's our answer. All right, so to me that is quite an easy question. All right, it's question 2, so usually the earlier ones are a little bit easier, but when you have a look at the mark allocation, so 57% of students got full marks, so that with the average of being 1.1. So, you know, a third of students got at least 1 mark. So you can see the working out there. Most students use the product rule, however, many erred with a derivative of log e 3x. So just make sure, I mean, it's such a basic antiderivative of logs are pretty simple. I think people get scared of logs, but they're not that hard, the derivatives. And common incorrect answers you can see there. So in part 2b, so you can see they're working, which is pretty similar to what I did. And this wasn't a hard integration by recognition question because you didn't, your integral was the same as the derivative. So we didn't have to do any manipulation. So 45% of students got 2 marks. So I think quite an easy question was done quite poorly. So students generally were not able to form an integral from their previous answer, ignoring the hence instruction. Some students attempted to integrate the given expression, some poor application of log laws. So you did need to know the log laws with that one as well. Okay, let's move on to the question from your trial exam. Okay, so this one was done quite well. So show that the point lies on the graph of G. So I might just write this and then we'll move on to part B. All right, so we've done our substitution. You do need to know your exact values for this question. So remember, sine squared is just squaring that result. So sine pi on 6 is a half. So a half squared gives you a quarter. And then multiplying that by root 3 on 2, which is the exact value for cos pi on 6. So as I said before, that question was done quite well. In question B, we're finding the derivative of sine cubed of x. So give your answer in terms of g of x. So some of you did that, and it's not actually that complicated. So, but just remember, if it's asking for a specific form, or your answer in a specific form, you give it in that form, okay? Because this question here is worth 1 mark. So if you didn't give your answer in terms of gx, you don't get that mark, even if you could find the derivative of sine cubed x. All right, so I'm going to use the chain rule for this one. So let u equal sine x. So that means y is equal to u cubed. So du dx equals cos x, and dy du equals 3u squared, which is 3u is sine squared x. So d dx is equal to, so we're just multiplying 3 sine squared x cos x. All right, so most of you are able to get that derivative, which is awesome, but we want it in terms of gx. So if we go up here and see, well, what is gx? Oh, all my stuff's gone weird. Okay, so there it is there. Okay, so you can see your answer for this one is just 3 times gx. Okay, because gx is equal to this part. Yeah, so that's gx. Whoops, need to shorten that. Didn't mean to include that 3. There we go. That part there is gx, so it's 3 times gx. All right, so for part C, oh gosh, don't know why everything's changed. All right, I'm going to have to restart. All right, I still feel like it's a little bit glitchy, but we'll see how we go. So in question C, hence find the area enclosed by G, the line y equals root 3 on 8, and the y-axis. So what we have here is an area between 2 curves. Okay, so some of you who were able to attempt this question forgot that you were finding the area between 2 curves, and you just found the area with the function g of x. Okay, so I'm going to just have to look at my notes because this one, I just don't want to miss anything. Okay, so we're going between, oh gosh, don't like that sound. Looks like a 6. Okay, from 0 to pi on 6. Now, the reason for that, oh, it's glitched. All right, so we'll start again, 3rd time lucky, and my neighbor has decided to use a chainsaw, so we'll see how we go with that noise in the background. Okay, so we're finding the area enclosed by G, the curve G, and the line y equals root 3 on 8. So remember when you see y equals any constant, that, oh God, that is really annoying. You hear it now? Let's stop talking. Okay, so that line just goes across like that, and that's at root 3 on 8. Okay, so don't ever forget that. And then we've got our trig graph. Now with this trig graph, it does cross, you don't know that it crosses at pi on 6. All right, so we, oh, actually, no, it crosses this line at pi on 6. So we're going to go from 0 to pi on 6. So the trig graph crosses the this line, y equals root 3 on 2 at pi on 6. So I'm not sure what the graph looks like, but let me just sketch a trig graph, something like that. All right, so we're finding this area in here. So that point there is pi on 6. All right, so the line, the upper line is root 3 on 8. Remember when we find the area between 2 curves, it's the top minus the bottom. So we're going to minus sine squared x cos x, and don't forget your dx on the end. All right, when you've got 2 lines like that, you can separate them. And for this one, it's probably easier because we kind of need to do that trig function separately. So I'm going to do 0 pi on 6 root 3 on 8 minus, and then we'll do the trig. And I know I'm not going to have enough room to do this, but all right, so writing out our antiderivative. So the first one, and we can actually do this all in one go. So let's just do the root 3 on 8. So any constant just becomes root 3, or whatever the number is, times x. And then we've got minus. Now, what we have with the trig function, you will see that it is a part of the derivative that we did in part B. So I've already circled the 3. So remember that 3 has to go there to make it the same, but we can't just change it without compensating. So I'm going to put the 1/3 out the front, because 1/3 times 3 is 1. So we're not really changing the value of that expression. We're just making it look a little bit different. Okay, so that when we're doing the antiderivative, the 1/3 stays, and then we know, all right, that looks like our derivative from part B. So our antiderivative of the derivative brings us back to sine cubed x. All right, so our original original function, sorry. And we're going from pi on 6 to 0. All right, so substituting those values in. So I might actually pause because this chainsaw is really distracting. All right, so for this question, you do need to know your exact values as well. So sine pi on 6 is a half, so that's where the half has come from. So you're cubing that, so 1/3 times 1 on 8. That's where the 1 on 24 comes from. In this second bracket, obviously you've got 0, and sine 0 is also 0. So we're just left with root 3 on 48 minus 1 on 24, and then bringing everything over the same denominator if you need to. There it is there. All right, just looking at the time. Let's see how we go. All right, so this question kept going. So the graph of G is dilated by a factor of A, where A is greater than 0, from the y-axis, and then reflected in the y-axis to become the graph of the function h. So we've got two transformations. We've been dilated by a factor of A from the y-axis, and then reflected in the y-axis to become h. So we have to write the rule for h. So first of all, we need to think about, well, what's happened to our points, our coordinates, sorry, x, y. So if we've had a dilation of factor A, okay, from the y-axis, that's going to affect our x coordinate, and then a reflection in the y-axis is also going to affect our x coordinate. All right, so dilation from the y-axis, so the x is going to become x on A, and then a reflection in the y-axis is going to multiply that by a negative. So with our function g, it's called h. So h of x is now equal to, so I'm just looking at my notes. So I'd have to scroll back to the previous page if I needed to substitute this into function g, because negative x on A. All right, so that's the rule for h with those transformations. All right, so the domain of h, so originally your domain of g was from 0 to pi on 2. So what we're actually doing is changing your domain of h. So first of all, we need to think about the two transformations. So we've had a dilation and a reflection. So because we're doing the domain, we're only considering the x coordinate. So your x coordinate has become now negative x on A, so similar to what we did here. So if I'm looking at my new coordinate for x, that's going to become negative ax. So with my domain of G, both the 0, so your domain of f now, we take the domain of G and just multiply it by negative a. So we're going to multiply that by negative a and multiply this by negative a. So your domain of f is equal to 0 times negative a is 0, and pi on 2 times negative a is negative pi a on 2. Now, with your domain, we should have the lower value first. So obviously we've got 0 and then a negative number. So I do, and a is positive. So your second value here is always going to be negative. So I do need to change that so that we have the lower number first. All right, so that was a bit of a tricky one to do, your domain. All right, how are we going for time? Cool. All right, so question E, let P be the x-coordinate of the left endpoint of the graph of H. Given that P is greater than negative pi on 4, find the possible values of A. All right, so with our domain, we know that P being the x-coordinate of the left endpoint, so it's going to be negative pi on A, negative pi a on 2 has to be greater than negative pi on 4. And then we're just solving for a. So negative pi a is greater than or equal to, so multiply by 2. So we're going to have negative pi on 2. And then we're going to divide both sides by negative pi, also multiply by so that's the same as multiplying by 1 on negative pi. So we're left with a. Then because we divided by a negative number or multiplied by a negative number, our inequality sign does have to change direction. So the pi's now cancel out and I'm left with 1/2. Now, we do need to find a lower limit for a. So we know a has to be less than 1/2, but in the previous question up the top here, it says a has to be positive. A is greater than 0. So we do have to have the lower limit for a as well. So a is any value between 0 and 1/2. All right, all good. Bye.